Right, hello everyone, and let's see, I got 7 of you guys online right now. We'll wait just a minute and see if everybody else can show up. But it's all right, if you can't make it to class on time, no big deal, because everything is going to be up on YouTube. You can always check it out on YouTube after the fact, no big deal, okay? So if you guys are on, you could just go ahead and say hi, whatever else you want to say. How's everybody doing? Everybody's healthy and well, I hope. And hopefully everybody's getting plenty of sleep. Get outside, get a little bit of sunshine, but don't go to any public places. You know, just take a little walk, get out in the sunshine when the weather's nice, but stay away from people, all that kind of stuff. Keep safe, and make sure if you are out anywhere else other than home, make sure you wash your hands and maybe even wear a mask. But again, avoid public places at all costs. Okay, so how's everybody doing? Okay. We are going to be talking about some more stoichiometry stuff. And so hopefully you guys, let's just move this over a little bit. Hopefully you guys have had a chance to figure out all the online stuff, to figure out Google Classrooms and all that. So please, if you guys need any help with Google Classrooms or any of that kind of stuff, ask me. And if I can't help, you got Mr. Vinton or Mrs. Cosgrove or something like that that can help you out, or Miss Martone. All right, so make sure you get all that stuff figured out, okay? We are going to be having a quiz sometime next week, probably next Tuesday or Wednesday, just to make sure we can figure everything out. Hopefully you guys are not going to have any problems with the homeworks and all that kind of stuff. So make sure you're able to get on Google Classroom, upload your homework, all that kind of stuff. Okay? All right. So let's go ahead and get started. Before we get started, please watch, or you should have already watched, your stoichiometry videos online. So there's Stoichiometry Made Easy. Right, we saw that a while ago. We should already be familiar with that. Stoichiometry with mass. All right, and the video for today, which I want you guys to make sure you watch, is going to be your stoichiometry grams to grams. So stoichiometry, it's going to be grams to grams tricks. Okay? Or it might say G2G. I forget exactly what the title is. But anyway, we're going to go through some stoichiometry problems today and go through a way that is going to make stoichiometry look a little bit neater rather than being 3 unconnected steps. We're going to try to connect them all together, make it look nice and neat, and hopefully help just solidify the understanding of how to solve these stoichiometry problems. Okay? So before we get going and solve a sample problem, and by the way, your sample problems, your homework is all up on Google Classroom. Make sure you go there for the document. The assignment is in Facts, but the document itself is always going to be in Google Classroom. Okay, so make sure you check that out. I'm going to go through problems 1, 2, and 3, and then you guys need to solve the rest for homework. Okay, so I'm going to solve like almost, half of your, or like a third to a half of your homework for you guys, and then you guys do the rest yourselves, okay? So, all right, so let's just jump right into it, if there are no questions or anything like that, and solve the first problem right here, okay? The thermite reaction is this reaction that's shown right there. It's a very useful reaction, a very hot reaction. Thermite is called thermite because it's so hot, gives off a lot of energy. In fact, it's so hot that it can even be used in terms of military, and so there's a thermite bomb that's used. But in order to make this fast enough to be an explosion type reaction, you need to have super small, like nanoparticles of your reactants, okay? Remember, we talked about how to make reactions go faster, and let me zoom in a little bit here. We've talked about how to make reactions go faster. So if we want to make a reaction of solids, remember this is a solid, this is solid. If we want to make a reaction of solids go faster, you make the particle size smaller. So you grind it up into a really small particle, okay? And so when you do that, you increase the surface area of the solids, and you can make the reaction go a lot faster. So this can be used in the military to make a super hot reaction. And it's also used, or it used to be used, for making just railroads. And so for attaching different railroad ties together, they would use this. Why? Because one of the products is iron, but not solid iron, liquid iron. It's literally so hot that the iron comes out liquid. And so it's a good way to have a portable reaction of iron coming out, and that iron can be used for welding purposes. So this is a very important reaction historically in terms of its use in making railroads. It's also used in the military, and it's it's just an interesting reaction in general. It's essentially like a type of single replacement reaction, and let's go ahead and just jump into solving this problem together. Okay? So the Thermite reaction is written here, and we say it asks us to calculate the mass of each reactant needed to produce 50 grams of liquid iron. Okay? So before we do that, we need to make sure that we balance the reaction. All right? So always, you got to balance that reaction before you do anything. And is the reaction balanced? Okay? No, the reaction is not balanced. We see we got 3 oxygens here, and we got 3 oxygens there. That's balanced. But we have 2 irons here, so we need to make sure we put a 2 in front of that. And we have 2 aluminums there, so we need to make sure we put a 2 in front of that. Pretty straightforward in terms of balancing this reaction. Okay? Next up, we want to solve for, so calculate the mass of each reactant. So this is really 2 separate problems. We want to calculate the mass of this iron trioxide and the mass of aluminum. We can start with either one. Let's just go ahead and start with the mass of iron trioxide first. So we want to figure out how much of that we have, and we start off with 50 grams of liquid iron. Okay? So yes, we're starting off with the products and going to the solve for the reactants, but it doesn't matter. All right? You can have any amount of any of these chemicals in the chemical reaction and solve for any one of the other ones. All right? So let's go ahead and do the first step, and that is to calculate the grams, all right? Because if you have, calculate the moles. So we're going to take 50 grams and convert that to moles. So the process here is we're going to start with, we're going to go from grams of one thing, so grams of, let's say, iron, and we're going to solve for moles of iron, right? That's going to be your step 1. Step 2, and that key step in stoichiometry is to go from moles of one thing to moles of another thing, right? You can only convert, when you're going from one chemical to another chemical, you can only convert from one chemical to another chemical when it's in moles, okay? So that's going to be going from, let's say, moles of iron to moles of, we'll solve for Fe2O3 first, right? And the last step is going to go back from moles back to grams. So that's going to be moles of Fe2O3 to grams of Fe2O3, okay? Now, sometimes you might not have the first step, and sometimes you might not have the last step simply because you're given moles or you're solving for moles, but when you're going from grams to grams, you have 3 steps. Moles to moles is 1 step, and grams to moles is going to be 2 steps, or moles to grams is going to be 2 steps. But grams of one chemical to grams of another chemical is always going to be 3 steps. So to solve this, the first thing we need to do is go from grams to moles of iron. And so we have 50 grams of iron. And we need to go and convert that to moles. So what's the conversion factor? How do we go from grams to moles? The molar mass, right? So we look at our periodic table, and let's move this down a little bit. All right, look at the periodic table. Hopefully you guys can see it. It's a little bit small here, but you guys all have periodic tables at home. All right, and if not, you can always look online. ptable.com is a great periodic table. But anyway, so we look at iron, right? It's 55.845, and that's going to be grams. So the molar mass here, if we're starting with grams, that molar mass should go on the bottom. 55.845 grams is 1 mole. Okay? Going from grams to moles, the grams of the molar mass is going to go on the bottom, and 1 mole is going to be on the top. Okay? So to calculate that, We multiply by numbers in the top, divide by numbers in the bottom, and ones we can simply ignore because 1 times anything is just itself. So this is going to be 50 divided by that 55.845, and that's going to be the number of moles of iron we have. All right, so I'm going to go ahead and write down 0.895, and I'm going to go ahead and include an extra significant figure. Why am I doing that? Because that's not my final answer. Yes, I only have 3 significant figures, but I want to include an extra digit here just so that my final answer doesn't have any rounding errors in it. Okay, so 0.8953 moles of iron. Okay, that's my first step. Next, we're going to go from moles of iron to moles of Fe2O3. So I just take the same number that I solved for already, and I'm going to write it down right over here. I'm going to get 0.8953 moles of Fe. And it's important that you write down both the units and the chemical so that you can keep track of everything. It doesn't take you but an extra second to do it. All right? It's going to be really, really sloppy and careless if you just write down the number. Okay? Don't do that. Write down the units, write down the chemical so that you don't miss out on anything. Because when you have just a bunch of numbers, it's so easy to get lost and see, okay, what in the world you're doing. So we're going to keep track of everything by always writing down both the units and the chemical. All right? Now, how do we go from moles of one chemical to moles of another chemical? We want to go from moles of iron to moles of Fe2O3. All right, that key middle step in stoichiometry always goes back to the balanced reaction. Okay? And so in the balanced reaction, we see that for every 2 moles of iron that you make, you need only 1 mole of Fe2O3, right? There's no number in front, so that's just going to be an implied 1. So what we do is, if we're starting with iron, right, and again, this is so useful that we write down the chemical. If we're starting with iron, that means that on the bottom, we're going to put Fe. It's going to, Fe and Fe are going to cancel out. And the number in front of Fe should be from the balanced reaction. So that's 2 Fe on the bottom, and if we're solving for Fe2O3, that Fe2O3 is going to go on the top. And that's simply 1, or you don't even have to write the 1 per se. Okay? So the 1 Fe2O3 comes, again, from the balanced reaction. So what you're starting with goes in the bottom of the conversion factor, and what we're solving for goes in the top. Okay? And so we can do that in our calculators. And rather than retyping this whole thing, right? Rather than retyping the whole thing, you don't need to. All you need to do is to type in, so it's multiplying by numbers in the top, dividing by numbers in the bottom. So all we need to do is divide by 2. So I hit in my calculator, divided by 2, and it automatically takes that previous answer. Don't retype it, all right? Just type in divided by 2, enter, and then boom, you've got your second answer. That hitting just divide by 2 saves you time in terms of writing stuff out and typing stuff out in your calculator, and it makes sure that you have 0 rounding errors, no rounding errors at all. Okay, so that's going to be 0.4477. Again, giving it an extra significant figure, just in case. Even though your answer really should only have 3 significant figures. Okay, so that's going to be moles of Fe2O3. Okay, now last step, we want to figure out how many grams of Fe2O3 is. So we have moles of Fe2O3, and we're going to convert to grams of Fe2O3. And in order to do that, we of course need the molar mass of Fe2O3. And so we're going to go ahead and calculate the mass, or the molar mass of Fe2O3. So we need to go back to the periodic table in order to do that. Okay, so back to the periodic table, and we have iron. So in Fe2O3, there's going to be 2 iron, so that's 2 times 55.845, and 3 oxygens, so that's going to be 3 times 15.999, and we add that all up to get the molar mass of Fe2O3. So that's going to be 2 times 55.845 plus 3 times 15.999, and and that's going to get us the molar mass of Fe2O3, which is 159.687. Units for molar mass are grams per mole, which means that what? It means that 1 mole of Fe2O3 has a mass of 159.687 grams. Okay? So that's our molar mass. You guys should be pretty good at calculating molar masses by now. Okay? But I know it's been a little while, so here we go. So that's our molar mass. That's our conversion factor between moles and grams of Fe2O3. And so last step, we want to take that moles and convert it back to grams. Okay? Can you see what you're doing again, please? Because I'm a little confused. Are you going to have to be specific about what your question is? Okay? So if you have any questions, make sure you're really, really specific about it. Okay? So let me just do this last step, then we'll go over any part that you guys are confused about. All right. Hi, Luke. Okay. So last step, you got 0.4477 moles of Fe2O3, and we're going to convert from moles to grams by using the molar mass. In this case, if we're starting with moles, 1 mole needs to go in the bottom, right? If we're starting with moles, 1 mole goes in the bottom, and that 159.687 grams goes on the top. And so last of all, let's just type that in our calculator, 0.4477 times, in this case, I can just use my answer of that 159.687, and that's going to get us our final answer for Fe2O3 of 71 point, we're just rounded off to 71.5 grams of Fe2O3. Okay, now I want to pause there and just see if you guys have any questions and try to explain any parts of this problem to you guys. Okay, so you can rewind it. That's true. You guys can go back and watch anything that you guys missed. He's finding the mole ratio and the grams. Yes, that's true. Okay, so any questions on what we've done so far? Let me just quickly review and tell you guys. The process is right up here, right? It's a 3-step to go from grams of one chemical to grams of another. The first step is to convert to moles using the molar mass. And the middle step, that key step of going from one chemical to another chemical, is to look up at the balance reaction and use the balance reaction as your conversion factor. And the last step is to just convert back into grams using the molar mass of that chemical that you've solved for. Okay? And so that's what we've done. This is step 1 right here. This is step 2 right here. And this is step 3 right here. And in the red, that is the molar mass calculation. So, any questions on this? This is for grams. So then what is the difference with finding mass and moles, etc.? Or is that covered in the video you posted? So the other video I posted is going to tell you exactly the same thing that I'm telling you right now, essentially. But let me see, grams to grams is the same as mass to mass. So grams and mass are the same thing. And when you go from moles to moles, that's one step. So basically, your general idea is this. The maximum and the most difficult problem that you're going to have to solve is like this, okay? If you have moles to moles, you're going to cut out step 1 and step 3, and you're only going to have one step, right? It's only simply going to look like, let me see if I can block this off. Your problem is only going to look like this. If you have moles of one thing and you're solving for moles of another thing, this is how you're going to solve it. One simple step, okay? If you have grams to grams is 3 steps, moles to moles is 1 step, and if you're going from grams to moles of another chemical, it's going to be, let's say, 2 steps. So you can, let's say, not do that step or not do that step in an easier problem. Okay? But I want to show you guys something in addition to this. Like, let me see. So Anna's saying, so do we do this for all the problems in the worksheet? No. So there's some other things you're going to do this. And also, why did you do it for Fe2O3? I did it for Fe2O3 because you have to do it for both of the reactants, and we're going to do it for aluminum here in just a minute. Okay, so next, what I want to do is I want to look at this problem, and I want to look at a different way to solve it. It's actually not a different way. It's simply a more concise way with exactly the same math. Okay? And so let me move this up a little bit so I can see a little bit more. Okay? So what I want to do is I want to say, okay, I want to do the same exact thing, but notice how I've got a little bit of redundancies, right? I've got this number 0.8953 and 0.8953. I've got 0.4477, 0.4477 written here, and I literally don't need either of those numbers for my final answer. So what I want to do is, rather than doing 3 different one-step conversions, I want to combine these 3 steps together to one big conversion, right? But the math is going to be the same, and the thought process is going to be the same, but it's going to look like this, okay? So I'm going to do it right here down in the blue, okay? So if I had this problem, right, I start off with my 50 grams of Fe, all right, and I want to solve for grams of Fe2O3. My first step is, once again, to convert from grams to moles, 55.845 grams, right? But rather than getting the answer and doing another step there, I'm going to combine these together and just right away do the second step, all right? And the second step is to go, let's do it like this. The second step is to go from Fe to Fe2O3 right away, okay, without actually getting that answer. And then we can put this third step on right here, right next to it also. So finally going from your moles to grams of Fe2O3, so you have 159.687. That's the molar mass of Fe2O3 over 1 mole, okay? So what I've done here is I've combined all 3 steps together into one, right? And notice what each step is doing, okay? This step here is essentially going from grams to moles, so grams of Fe to moles of Fe. This middle step is going from moles of Fe to moles of Fe2O3. And the last step here is going from moles of Fe2O3 to grams of Fe2O3. So same exact process, but I'm going to make it a lot more concise and make it all in one thing. All right? So then you can cross out, exactly. So what do I have? I have grams over grams cancel out. I have iron over iron cancel out. I have moles over moles cancel out. And my answer is going to be grams of Fe2O3. The math is going to work out exactly the same, and let me show you how that works. So rather than doing it in 3 separate steps, we can do it all in one. And watch how I do this, okay? So let me zoom in a little bit more. So watch how I do this math. So if I'm starting off with 50 grams, I multiply by numbers in the top, divide by numbers in the bottom. Ones you can basically ignore because 1 times anything is just that anything, okay? So it's going to be 50 divided by 55.845. All right, no parentheses necessary, divided by 2. Why? Because that's on the bottom. And then times 159.687. Okay? Just multiplying that. So all in one shot, hit enter, and my answer is exactly what I expected to be, and that's going to be the 71.5 grams of Fe2O3, okay? So this is going to be an easier and a lot cleaner way to solve these stoichiometry problems anytime you have grams of one thing to grams of another thing. And in general, you'll notice that you've got at the top here 1 mole, so the top left 1 mole, and the bottom right 1 mole, and over here is going to be the molar mass of what? This is the molar mass of the thing you started with. On the top right, this is going to be the molar mass of the thing that you're solving for. And right there in the middle, that key step for stoichiometry, on the top is going to be the thing that you're solving for. And that's going to be coming straight from the balanced reaction, right? So we have 1 Fe2O3, straight from the balanced reaction right there. And on the bottom is going to be what you're starting with, and that's going to be coming, once again, straight from the balanced reaction. Okay? So you guys can solve these problems like this, and it'll really save you guys some time, and I think it'll make it nice and neat so you guys can see what's going on a little bit better. But what I want to do is I want to go ahead and solve the second part of this problem using this method. Okay? And so the second part of this problem says, let's see, calculate the mass of each reactant. So the second part is we need to solve for aluminum. Okay? So let's go ahead. I'm going to flip this over. We're going to go ahead and we're going to solve now for aluminum. Okay? So starting all the way from the beginning of the problem. All right, 50 grams. 50 grams of Fe. All right? And the first part is to convert from grams of iron to moles of iron. So we want to convert to moles. So we put 1 mole on the top left. And in order to convert to moles, we need the molar mass of Fe. That's going to be your 55.845. Again, getting that number from where? From the periodic table right below iron. You find that number. That's the molar mass of iron. Okay? Next step. If I want to figure out the amount of aluminum made in this case, or the amount of aluminum needed in this case, we're going to, starting with iron, right? We're going to put 2 Fe on the bottom. Why? Because if I'm starting with iron, I've got 2 Fe here in the balanced reaction, 2 Fe goes on the bottom. And if I'm solving for aluminum, it's going to be 2 aluminum right there in the bottom. Or I'm sorry, right there on the top. So 2 Fe on the bottom and 2 aluminum on the top because I'm solving for aluminum. Last of all, why am I solving for aluminum? Because the problem asked me to. Okay, so back up here, what am I doing? It says calculate the mass of each reactant. Each reactant, that's a reactant, and that's a reactant. We already solved for Fe2O3, now we're solving for aluminum. Okay, so last of all, we need to go from moles of aluminum to grams of aluminum. And the way we're going to do that is we need the molar mass. And so 1 mole is going to go in the bottom because we already have moles and we solve for mass. So we go back to the periodic table and we look up aluminum. That is right there, right below aluminum is 26.982 grams. Okay? Use your calculators for this. And once again, we're going to be just typing it all in one line. 50 divided by 55.845. And now we have times 2 divided by 2. So you really don't need to put anything in for that, right? 2 over 2 is simply 1. But if you want to, you can do times 2 divided by 2. Okay? But that's superfluous. It's not necessary because 2 over 2 is simply just 1. Okay? And then last of all, times 26.982, the molar mass of aluminum. And that's going to be our final answer for that part, for aluminum. So that's going to equal 24 we're going to round it off to 24.2 grams of aluminum. Okay? And notice how things can really cancel out here. Okay? Notice that if we're starting with iron, our iron, so iron and iron are going to cancel out. If we're starting with grams, grams over grams are going to cancel out. And then we solve for moles. Moles over moles are going to cancel out. And we're left with what? We're left with grams of aluminum. So this setup really, really shows you what those units are doing. Okay? So now I got some questions here. Let me see. So let's see. Why did you put 2Fe on the bottom of 2Al? These things right here, again, are coming from the balanced reaction. How do you know which one's on the top, which one's on the bottom? 2 ways. 2 ways. First of all, whatever you're starting off with must go on the bottom. Okay? And whatever you're solving for must go on the top. So this is the the chemical that we are starting with, right? And this is the chemical we are solving for, okay? Secondly, you can notice that everything cancels out. So if you actually follow my directions and write down the chemical here, you'll notice that if you start off with iron, you need to put iron on the bottom so that they cancel out, okay? And so aluminum is going to be on the top. It's not going to cancel out, and you'll end up with what you want to end up with, and that's aluminum, okay? All right, let's see. 48 point, just kidding. Why did you, okay. So got a couple questions about top and bottom. I think that I answered that. Any other questions on this problem? Okay. If there's no other questions on this problem, we can solve one more together. So I'm going to solve another one of your homework problems. And once again, if you have no idea what I'm actually doing, these are your homework problems that you can find in Google Classroom. You guys should have already opened it up and gotten the document, and you can just literally follow along and write these answers down as we go, so that I've already solved 3 of your problems for you guys, okay? So, looks like no more questions there. All right. Can you do number 2? Yes, that's exactly what I'm going to do. I'm going to do number 2 and number 3 together. Right here. Here we go. Would you record this? I am recording this live stream. Okay. And so you guys can come back anytime and rewatch this. If it's too fast or too slow, you can speed it up, slow it down. That's what I love about YouTube. I love to watch things super fast. I love it to watch it like 2x speed. But if it's too fast for you, you can always slow it down. So whatever you guys like. YouTube allows you to change the speed as you like. I love that, and you can always come back anytime you want. So anyway, so diboron trioxide. So we're here, number 2, number 3. They go together. So let's just go ahead and do this one. Diboron trioxide reacts with hydrofluoric acid. This is diboron trioxide. You might not know hydrofluoric acid because we haven't covered acids and bases yet, but you can see it, you can kind of guess, okay, you know that this is diboron trioxide, so the other reactant must be your hydrofluoric acid, that HF. Just a little heads up, we're going to cover, let me zoom in on this a little bit so you guys can see this a little bit better. Okay, we're going to cover acids and bases in the next unit. So just a little heads up, a little forewarning, that H in front helps you know that that is an acid, okay? An H in front helps you know that that's an acid. And so, anyway, that's not a part of this unit though, okay? So diboron trioxide reacts with HF, reacts with hydrofluoric acid to make boron trifluoride and water, okay? So before we do anything, of course, we need to balance that reaction. So let's go ahead and balance the reaction, all right? If we have, probably the easiest place to start would be boron. We got 2 borons there, so we need to put a 2 right there in front of boron trifluoride. All right, and then next up, we see, okay, somebody else has balanced this for us. That's awesome. So next, once we do that, we notice that that's 6 fluorines, so you can put a 6 right here in front of HF, right? And also, we have 3 oxygens here, so we need to put a 3 in front of H2O. We haven't looked at hydrogen yet, so we need to make sure that that's right. So 3 times 2 is 6, and that's 6 hydrogens there. So everything is nice and balanced right now. Okay? So that's the balanced reaction, and let's go ahead and solve number 3 here. What mass of boron trifluoride can be made from 2.75 moles of diboron trioxide? Now, this problem is a little bit different, right? Because what's it asking us to do? It's asking us to go from moles of boron of B2O3, and we're solving for a mass. Mass always means grams. So we're solving for grams of BF3. Which means this is a moles to grams problem, which means that's going to be a 2-step problem. So the same exact setup that we've been doing for 3 steps, we just removed one of the steps. All right, so let's go ahead and see what that's going to look like. Okay? Yep, just 2 steps. So always, we're going to start off by writing down this amount, the amount that we know, the amount that we're starting off with. 2.75 moles of what? Boron, diboron, trioxide. But it's already moles. So that means we're literally skipping the first step, okay? So if you already have moles, you skip the first step. You skip that moles to that grams to moles step, okay? So you already have moles, so we're going to skip the first step. We're going to go right to that middle step. And that middle step is going to be what? So we're going to go from moles to moles of B2O3 to moles of BF3. That's going to be our middle step, okay? And how do we do that? We look back at the balanced reaction, okay? The balanced reaction says, all right, for B2O3, if we're starting with B2O3, we need to make sure that B2O3 goes in the bottom, and there's no number in front, so we can just put a 1 there, okay? But we're solving for what? We're solving for BF3. So we're going to put BF3 on the top, and we go back to the balanced reaction, and we see, okay, there's 2 BF3 right there at the top. So that's going to simply be, all right, we're going to, actually, we could do it step by step, but I want to go ahead and do 2 steps here together. Okay? So we could solve for the moles of BF3 and then calculate the grams, but I want to go ahead and put this together like we did on the last one. Okay, so we've gone from moles of B2O3 to moles of BF3, and last of all, we want to go from moles of BF3 to grams of BF3. And anytime you're going from moles to grams, you're going to need the molar mass, okay? So we need the molar mass in order to do this, and it's going to be the molar mass of what? The molar mass of BF3. And so let's go ahead and calculate the molar mass of BF3. Looking at your periodic table, we can look at the periodic table and find borons right there. And there's 1 boron. Boron is 10.811. And BF3 has 3 fluorines. So 3, and fluorine is 18.998. All right, we're going to add that all up. That's going to get us, oops, sorry. So we got, this is the mass, the molar mass of boron. This is the molar mass of, right there, fluorine. We got 3 of them. So let's go ahead and type that in for the molar mass of BF3. That's going to be 10.811 plus 3 times 18.998. That's going to get us the molar mass, which is 67.805 grams per mole for BF3. Okay? So back up here. This number, where's it going to go? Is it going on the top or on the bottom? What do you guys think? All right, what do you guys think? All right, look at some questions here. So just 2CS. Why did BF3 go in the top? BF3 goes in the top because we're solving for BF3. Always the chemical you're solving for goes in the top, and the chemical that you're starting off with goes in the bottom. Okay, and so top. Those of you guys who said top are absolutely right. This molar mass is going to go on the top. Why? Why? Because we're starting off with moles, which means we want to cancel out the moles, so 1 mole goes on the bottom. Or another way to think about it is we're solving for grams. So grams must go on the top. So we have 67.805 grams on the top. The molar mass goes on the top when you're solving for grams, and the molar mass goes in the bottom when you're solving for moles. But in this case, we're starting with moles. Moles and moles cancel, and we're solving for grams. So let's do the math. And that's going to be 2, let's see, move this over here, 2.75, right? Multiply by numbers in the top, divide by numbers in the bottom. So that's going to be times 2 divide by 1, but you don't need to divide by 1. You can basically ignore the ones. And then multiply by the numbers on the top, so that's 67.805. I can literally just type second answer because I just got that number right up here, okay? So that's 2.75 times 2 times 67.805, enter, and that gets me the mass of BF3, and that's going to be 372. 372, well, actually 373, we're going to round up to 3 significant figures. So 373 grams of BF3. And that's going to be our final answer, okay? That number might look a little bit big, but remember, we're starting off with moles, and 2.75 moles is quite a lot. So it's not surprising that it's this much. Okay, so questions. Anybody have any questions? Questions? I know there's a little bit of a time lag, so maybe you guys are still listening and just now hearing it, something like that. So questions. Why just only 372? All right, why? What do you mean? You mean why can't we can't see the answer? You can't see the answer. What can't? Because you rounded. Yeah. So why is it 373 rather than 372? So if you look, you guys should be able to see my calculator. Notice right here is 372.9275. The 9 is going to round up because we only want 3 significant figures. Why? Because we have 3 significant figures here. Now again, I don't want you guys worrying about significant figures, but that's why, okay? We should only have 3 significant figures because we have 3 significant figures here. And anytime you have a 9, you're going to round up, okay? So 5, 6, 7, 8, 9 rounds up. 0 to 4 is going to round down. Okay. Any questions? Any other questions? I think we're all out of time. You guys probably have another class to go to, something like that. So finish this up for homework. We'll go over the rest of the homework problems on Monday, but please finish this up for Monday. Watch the other video. You're welcome to rewatch this one if you want to. If you guys have any questions, post the questions on Google Classroom, and I'll be looking there. Anyway, have a wonderful rest of your day. See you guys